Alright, welcome to the video for 8.1 Geometric Sequences. Okay, so this chapter is kind of a hodgepodge of two things. It is the series and sequence mini chapter, and then we also have our modeling with volume and density chapter. So, kind of long. This first half is about the series and sequences. Okay, what the heck is a sequence? A sequence is a list of numbers. The most classic of the lists of numbers, 1, 2, 3, 4, ... right? The very first list of numbers you ever learned, you're counting numbers. Now, that's not our only series of numbers. We've got 2, 4, 6, ... We've got 2, 4, 8, 16, ... We've got 1, 1, 2, 3, 5, 8, 13, ... That last one is very famous. It is the Fibonacci sequence. Okay, but these are all sequences of numbers. What they have in common is a pattern, right? This first pattern, adding 1. Super exciting pattern. Second pattern was adding 2. The third pattern wasn't really adding, it was multiplying by 2. So let's kind of write this down. Plus 1, plus 2, times by 2. And then the Fibonacci sequence has a fancy pattern. It's you take the first two numbers, you add them together, you get the next one. Then you take the next two numbers, you add them together, you get that one. So 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 13, the next one would be 21, so on and so forth. So add previous. The types of sequences we're going to focus on are the multiplying patterns. So for example, 2, 4, 6, or 2, 4, 8, 16, we could have 1, 3, 9, 27, and then also kind of a dividing pattern as well, although we consider it multiplication by a fraction. So we could do, I don't know, 10, no, we'll do 100, 50, 25, ... That would be dividing by 2, right? But really it's multiplying by 1/2, okay? So those are the kind of ones we're going to focus on, not because they're the most exciting, but because they lead into series really well. So, all right, cool. So we're going to jump down. There's some technical stuff, but let's start with some exercises. Find the missing terms of the sequence. So we've got this sequence here. It's definitely not 1, 2, 3, 4, 5. It's 1.2, 3.6, 10.8, 32.4, and then it has this A5, A6, A7 thing going on. The missing terms are these subscripted ones here. Okay, now why 5, 6, 7? Because that's the place number. Okay, that's where you see 1, 2, 3, 4, oh, 5th, 6th, 7th. So for technical purposes, so we don't have to confuse ourselves, we're just going to use that subscript notation to talk about the place number, the term like place number. In general, we give that n. Okay, so the n is the place number. The A part is the actual number. For example, I could say the first term, so n equals 1, but then A1 would be 1.2. Okay, A3, the third place, but that actual number is 10.8. Okay, all right, so now how are we going to figure this out? Well, we also need to find our R. What the heck does an R stand for? Our R stands for our common ratio. Common ratio. It's a fancy word for the pattern. It is the common thing in between each one of these. How on earth would I figure out what we're going by? I could jump to a calculator, divide 3.6 by 1.2. Oh, I found that to multiply by 3. Double check 10.8 divided by 3.6. Ah, that's also times by 3. So times by 3 each time. Our common ratio, our pattern. Sorry, my pattern looks really weird. Spell that right. Pattern would equal 3. Super fancy, but that doesn't help me exactly. That's not the answer to my question, right? The answer is what are the next 3 terms. So we times by 3 now. We get, let's see, 30, I can't read that. 32.4 times 3, 97.2. From there, we times by 3, we get 291.6, and then we times by 3, It's 874.8. And we have found the other three terms. Okay. All right, cool. This is basically just called counting or recursion. You just count to the next one. Super fun. Find the specified term, an, given the first term and the common ratio. In other words, find the explicit equation. So, with patterns, we can also set up a general formula for them, okay? This pattern we just had, well, it started at 1.2, and then it times by 3. If I just say this pattern is timesing by 3, that doesn't really give me enough information to write the whole sequence down. If I just say timesing by 3, well, that could be 3, 6, 9, 12. But that's not the sequence you see on the page, right? So I need to state kind of two things. I need to state what is the first term. Oops. And what is the ratio? Okay, so what is the first term and what is the ratio? If you list those two things, you can actually create you can create the exact same sequence. In that last case, it was 1.2 and 3. Here, they've also done that. They've listed that the ratio is 1/2, and then they're showing us the first term is 128. Okay. Now, what does this mean for an equation? They want us to give us an explicit equation. How does that work? Well, what we can do is build kind of a generic equation for any an with this multiplying pattern. We would start with our first term, a1, and when we keep multiplying it by that pattern, right? We'd multiply and multiply and multiply and multiply it. In fact, we would multiply it so many times that we would multiply it to an exponent amount of times. Repeated addition becomes multiplication. Repeated multiplication becomes exponents, right? So the third term would be a1 times r times r times r. The fifth term would be a1 times r times r times r times r times r. Okay? The problem with this is that if I go just with n as my exponent, I'm going to be one term off because my first term wasn't multiplied by that 3. 1.2 was never multiplied by the 3. So I have to adjust it a little bit. I say n minus 1. Okay. The only reason we do that is because the first term was not actually multiplied by that r. So we have one less. So if I wanted to find the fifth term, I'd actually be multiplying r 4 times. If I had the eighth term, I'd be multiplying r 7 times. And you can see the pattern keeps going. So the easiest thing to do is just take off an exponent, n minus 1. All right, so over here now, that means our pattern, an, for this sequence starts at 128. That's our a1, our first term. And we're going to multiply 1/2 n minus 1 times. That's going to be our general formula. It's not just the one for n equals 8, but it's our general formula. Now we can kind of plug in n equals 8. So a8 would be, and just like any other equation, all the n's are going to change to 8. 128 times 1/2 to the 8 minus 1. Okay. That's not really an actual number, though. So why don't we go ahead and, actually write the number down. Exponent rules, my friends. People can set up beautiful equations, but then do this wrong because they try to do 1/2 to the 8th. Exponents got to come first. So 1/2 to the 7th. 1 over 2 to the 7th power is 1 over 128. I'm going to have to write down here. So we have 128 times 1 over 128. Oh, hey, look at that. This is going to equal 1. So after our 8th term, after 8 times, our 8th term is actually going to go all the way down to 1. Cool. Let's do another one. Given the geometric sequence that follows, write the explicit formula and find the 9th term. What the crap? The geometric sequence? What the heck does that mean? Geometric just means multiplying pattern. It's the ones we've been working with. Okay, so if we say the geometric, it just means a multiplying pattern. The adding patterns are called arithmetic, if you remember that throwback to freshman year. And then the Fibonacci sequence that didn't have its own special name is called the Fibonacci sequence instead of a geometric sequence, right? And other patterns, there are other names, but those are usually the 3 you see people work with. So they're just telling us here it is a multiplying pattern. You don't have to worry about it actually subtracting, so go ahead and find that one. It says write the explicit formula and find the 9th term. So oh, sorry. In the last problem, they were kind enough to give us all the pieces. Here, they didn't list all the pieces, but at least they gave them to us all. What is A1? Well, remember, A1 means the first term, so that'd be the 32,768. It's our A1. Our ratio we're going to have to figure out. Well, it's going down, so I know it's a fraction. It's dividing something out, so let's see if we can figure out what that is. Let's do 8192 divided by 8192 divided by 32678. As a fraction. Nope, just kidding. Okay, do that and I get a 0.2 decimal place. So that doesn't really help me, right? Let's see if we can divide the other way around. 8192. I get that it's to get from 8192 to back up to 32,768, I had to times by 4, which means to get there I had to divide by 4. So 1/4. Okay, so 1/4 is what the common ratio is. We're dividing by 4 each time. The reason we want to go with a fraction is now because of this equation, right? We could write divided by 4. We'd all read that the same way, but you can't plug a divided by into an equation. So we're going to make it as a fraction. And then they want us to find A9, but until we have an equation, that's going to take a lot of work. So let's just make an equation. AN equals 32768 1/4. And again, we want to make sure we're not multiplying too many times. We have to kind of counter for the fact that it's 32,000 never actually did get divided by 4. It was the first one, and then to get to the next one we had to divide by 4, so we put in that -1. And we have our explicit equation. Explicit just means explaining. All right, A9. Let's plug in 9 now. Oops, pardon me, that was a 2, not a 3. 9 minus 1. And again, we'll follow our PEMDAS rules, which says exponents first. Okay. Looks like 1/2 is where we will be. So this one's will in fact divide so far down that we end up going into the fractions slightly. Okay. Let's work with these a little bit more. We got a couple more examples, kind of around the same idea, like finding a lot more pieces and then kind of a word problem. But this is basically the logistics of sequences. Excuse me. Alrighty. That's more here. Find the missing terms in each sequence. State the common ratio. Okay. Let's start with actually the common ratio because we can't find the terms until we know the pattern, right? So let's see if we can find the common ratio between these guys. Well, again, it's going down, so I think I'm dividing. The first two may not be the place I want to look. Maybe that's not the easiest place to see. I'm seeing right here, that looks like it's dividing by 2. So maybe we're looking at 1/2. Let's double check though. Is 352 divided by 167? That's also 1/2. So it looks like common ratio is equal to 1/2. Fabulous. Stated the common ratio. Now I can find A5, A6, and A7. Divide 44 by 2, or times 44 by 1/2, same thing. 22, then 11, one more time, 5.5. And we have found it. Cool. Not all of these are going to be super easy to read right now. We now have a fraction within our sequence, right? How do you get from 7/3 up to a whole 7? Let's look at this a little differently. 7/3 up to a 7/1. Well, the 7 part didn't change. It's the 3 part that went away. So, how would I get rid of a divided by 3? Oh, I times by 3. Again, that may not be the easiest place to look, but if all of your terms are fractions, that may be a helpful hint. If you have fractions within a sequence a lot, you may want to look at the pieces of the fraction. Here, nothing changed, but to get from there to there, I had to times by 3. So it looks like our ratio is 3. That is confirmed by the fact that 7 to 21 is times 3, and 21 to 63 is times 3. So my ratio is definitely 3, no matter where I'm looking. All right, so A5 would be times by 3, 189. Times by 3 again, a 6. Our sixth term is going to be 567. And our seventh term is going to be 1,701. Cool, we have found our terms. Find the specified term, an, using the given information. So once again, they've given us the information. We're going to go through and we're going to actually create an equation out of it and then plug in. And you're saying, Miss K, why can't I just take this number and use the ratio that many times? Yeah, it would work. It'd work especially if you have to find a lot of them. But if you don't need to find a lot of the numbers, you will probably want to use the equation. If n equals 100, you're going to be sitting there all day multiplying that number over and over and over again. If we had an equation, we can just jump straight to 100. So really, at the end of the day, they both hold merit. Here, simply just counting, or what we call recursive thinking, it's very, very useful. Here, the equation, when it's all the way up at n equals 9, and we're starting at 0.14 anyway, that's going to take me some time if I don't use an equation. So let's see if we can creep up. Let's see if we can create an equation. An equals 0.14 times 2 to the n minus 1, right? Don't forget that n minus 1 part. And now we want to plug in 9. So a9 would be 0.14 times 2 to the 9 minus 1. In other words, 2 to the 8th times 2 to the 8th would be 35.84. That would be our ninth term. Okay. Let's do it again. Even though 6 isn't that far up, I'm still dividing by 4 each time, and after 4 times, I know that, or after 3 times, pardon me, I know 64 goes to a fraction. So still, an equation might be even more helpful. 64, 1 over 4, to the n minus 1. We get 64, pardon me. That's just our general format equation. Now we need to plug in the sixth term. 64, 1 over 4 to the 6 minus 1, or 64 times 1 over 4 to the 5th. 64 times 0.25 to the 5th would be 0.0625. Change that to a fraction. We get 1 over 16. 1 over 16 would be our term number. Now, can I leave it as a decimal is always my question. If your sequence has decimals in it, yes. If your sequence does not have decimals in it, no. If your sequence is already going by fractions, you need to list your answer as a fraction. The reason for that is because of practical application. Okay, if for some reason the sequence has already been chosen as a fraction, you need to write it as a fraction as well. Okay. Write the explicit formula for the sequence and find the specified term. So we need to write the explicit formula. We've been doing that for 3 problems now. Let's see. Our first term is 6. I don't know. Not really sure of my ratio here, but I know that there's an n minus 1 up there. Okay, so these are the pieces I can pull straight out. Now, how do you get from a 6 to a 9? Well, a 6 to an 18 would have been 3. That's not going to work. But half of that? 2? Okay. Maybe I'm not seeing it there. Let's look over here. Let's look at the fractions. From here to here, multiply by 3. Right? From here to here, we multiply by 3. From here to here, we multiply by 2. So maybe 3 halves is our ratio. Let's try it from 6 to 9. 6 times 3 over 2. It is actually 9. So then we get 3 over 2 as our ratio. And yeah, it doesn't have to be a whole number. It doesn't even have to be a fraction. It can be something totally weird. But some pattern is hidden in there. All right, now we're going to use that to find the 7th term. I'm going to plug it in. Okay, once again, we're going to do our exponents first. So 6 times 3 over 2 to the 6th. We get something that's not a fraction. So then we change it to a fraction, 2187 over 32. All right. If you do not know how to change a decimal into a fraction via the calculator, then hit up any one of the math teachers in the math department and they will show you how. It depends on your calculator, so I'm going to say go see them with your calculator and they can show you. Maybe the sub knows how to as well. If they do, they can let you know. All right, where on earth are we going to use any of this crap? So, a type of bacteria doubles in number every day. If you start with a culture of 50 cells, how many cells would you have after 8 days? What is the formula to determine how many cells you would have after n days? All right, so we have kind of a situation here. We can see that the pattern, we don't really know yet, but it says we start with A1 would be 50 cells. We need a ratio because I'm seeing a pattern like situation here. It's growing, it's moving, and I'm going to get some more. Every day I'm going to have a new number. Every day it's going to be bigger. It's a sequence. What would be the ratio here? The ratio is actually not listed as a number. It's listed as a word. It doubles every day. That's it. It doubles. And so our ratio would be 2. We're timesing by 2 every day. Tripling would be timesing by 3 every day. Down by a half, your ratio would be a half. It cuts out a third every day. That would be a third, right? So you can see how sometimes it's the context that'll tell you that ratio. All right, how much will we have after 8 days? We could do this old school. We could just take 50 and keep dividing for 8 days. That might take a while though. If I make an equation, it might go a little faster. So first term, ratio, n minus 1. Plug in my 8 days. I don't want to do 1/2 to the 8th. I'm going to do 1/2 to the 7th. 50 times 0.5 to the 7th. We get about 0. Well, let's do it as a fraction. Okay, 25 over 64, or 0.4. Oh, I'm sorry. Why did I put in a half? I'm sorry. Okay, I'm confusing myself. I was like, why is it going down? That's not a half, dear. That would be doubling. 2. Okay. Silly Miss Kennedy. You're probably like, Miss K, stop. You're ruining the video. No, it's a 2 there. Just kidding. So plug in 2 and 8. We get 2 to the 7th times 50. That makes more sense. Okay. 6,400 bacteria. Because it's going up, right? Sorry about that. Okay, so 6,400 bacteria after 8 days. What is the formula to help determine how many cells you'd have after n days? Interesting. N is already the variable in here, and so it looks like this would be our formula to determine how many cells we'd have after n days. If I already set up that formula, I've already answered that question. Okay, so this actually was all from Secondary Math 1. It's kind of why I breezed through it a little bit. If you have any questions, let me know via email, or you can let the sub know. The key point of this is the definitions here. Your ratio, your AN, your A1, you're going to see those throughout the rest of this chapter. So make sure you know what those mean and make sure you know how to complete the terms. Other than that, I'll see you in 8.2.